Okay, so here is my problem. I'll read it. The bridge below is made up of structural steel with a Young's modulus of 200 gigapascals and a Poisson ratio of 0.3. So that's just structural steel. The cross section of the truss is a circle with a diameter of 25 centimeters. The dimensions of the truss are shown below in the diagram, and they're horizontally symmetric about the middle of the bridge. And they're also mirrored about the center of the bridge so that the truss flanks the roadway like on a normal bridge. And the truss joints at the top are connected by bars of the same cross section going into the page. The base of the bridge is 20 meters long with a height of 1 meter and a width of 6 meters. The force of 13.5 kilonewtons is supposed to represent a pickup truck traveling across the bridge. So in the problem, I basically plan to just apply it to like split the top of the bridge up into a bunch of faces and apply the force to each face over time to kind of approximate the truck going across the bridge. And I also had Googled the weight of a pickup truck, and 13.5 kilonewtons is just about right. And yeah, so the goal is to approximate the maximum deformation and max stress in the bridge using transient structural analysis and make ANSYS produce an animation of the deformation over time. So, the key word here is approximate because it is very challenging to get a force to change position continuously over time. Like it's really, I was only able to figure out how to do it in discrete steps using tabular data. So yeah. All right. And then some other like assumptions I made is just that the whole thing is made of steel. And I recognize that the bridge base itself being made out of 1 meter thick steel is like not realistic and definitely overkill for like a pickup truck, but it reduced the complexity of the problem, and my computer is not like, and neither is the VM. The VM or my computer aren't really up to the task of solving anything much more complex. Okay, so getting into ANSYS, I've already solved the whole problem, so I'll pretty much walk through what I did. So I'll go into the design modeler and show how I built it. So the base is a 3D just rectangular prism, and I made it with this sketch and I extruded it. Then I extruded these squares into the bridge, but not with any depth, just to make just to imprint faces over here. You can do that operation. So that allowed me to, apply the force to each face over time. And then these are just the lines I drew for the truss. And then I turn them all into a line and then use this cross section on them, just a circular cross section. So yeah, and then so there are two parts, two bodies. So there's the solid part and then there's the line body. And I'll show you like getting ANSYS to kind of combine them was really tough. Initially, I was getting problems where when I went to solve it, the truss was just not connected to the base of the bridge, and all the loads were just being applied to the base of the bridge and weren't at all transferred into the truss structure. But that's when I realized I had to make joints. So again, here we have solid and line body. And so they're both structural steel, like I said earlier. And yep. Let's see. So yeah, here we go. Connections. I made a bunch of connections and they're all set up basically the same. So they use the face as the reference and then the vertex at the end of the line as the mobile component. And then I'm using a pinball region of 500 millimeters, and that's to accommodate the testing I was doing with like pretty large elements to see if how they converged on a solution. in terms of max stress. And the behavior is deformable, which isn't actually necessary, but I was doing some research and that was what seemed to be most advisable. And oh yeah, I had to make a new reference coordinate system for each joint, as you can see. So yeah, that was kind of tedious, but it's okay. I was thinking about using symmetry, but when I actually went to solve the problem, it wasn't necessarily perfectly symmetric. Like there, because oscillations arose, so it kind of caused the bridge to wiggle a little bit um, about both axes. So then, so this is just one of many iterations I've done in terms of mesh size. I did runs with 700 millimeter element size, 500, 300, 200, and 175 millimeters. Once you, so initially also you can set the analysis settings up and change the step size. So this is the biggest I ever made. This step was 0.025 seconds. All of the element sizes above 200 millimeters, well, including 200 millimeters, were simulated at 0.01 seconds, so a smaller step. So you get a more granular output, but I just wanted to test like a smaller element and see if it gave me different outputs. So I had to increase the step size or else ANSYS would give me like errors. Basically saying, oh, this is taking too long. You need to upgrade your license to a high performance license, which lets you use more of your CPU. But obviously I'm not going to do that. So I had to resort to kind of large step sizes and fairly large elements. So here we'll go to the boundary conditions. So this was supposed to be, if you look at the problem, like rigidly supported at both ends. So I guess this would be an indeterminate beam if we were in mechanics of materials. So if we go back here, the way I modeled that was using frictionless supports at both ends. So that restricts rotation about the z-axis and the y-axis, and also restricts movement in the x direction. And then I also put displacements of 0 in the y direction on the bottom line over here, so it couldn't really move up or down. But also trying to avoid any weird stress concentrations on the end. So let's see, where's the other one? Yeah, and then here's the other one on that end. And then also a displacement in the z direction of 0 for this point right here, for this vertex. Yeah. And then here are the forces. So down here you can see it's all in one step, and I vary the force every 2/100ths of a second. So if we go down, that's what it looks like. You know, maybe not the best approximation, but it is the most frictionless way I could figure out how to do it and like get a somewhat desirable result. So let's see, I'll show you the solution. So here you kind of see in the deformation graph that we get a lot of oscillation actually. And this is way more pronounced if we have a smaller step size actually. So I'll just play this right now. And I have it, notice the scaling up here is like, let's see, about 100,000 times. So this bridge wouldn't actually deform this much. Like the maximum deformations are in 10⁻⁴ millimeters. And that's really just because of the bottom, I think, being solid steel. So yeah, and it's kind of rendering right now, but yeah. So yeah, we see a peak of 4.0234 times 10 to the negative third. And I want to show you how it oscillates way more in other situations. Let's see. Oops. So let's see. Here's like, it clearly oscillates a lot more when you make the time step smaller. And again, this is kind of a useless like visualization. It was just, for whatever reason, ANSYS automatically scaled the displacement by about 10 million times. So that's why you see that wiggling so weirdly. But I also found that quite amusing. And then if we look at, I also have an Excel file pulled up here of how the solution converges at different element sizes. So like ideally we'd use way more elements, I think, because here you see it it seems to maybe be converging around here at larger element size, but then you get smaller and then you see a spike over here in the maximum principal stress, and then it dives back down. So I think ideally we'd probably want to increase the amount of elements and try at different, more different element sizes. But as it stands right now, it takes about an hour to simulate this problem at these two element sizes over here. So it's not really feasible for me to do that. But yeah, the model I'm showing you right now is at the smallest element size I was able to use. And then you also, of course, run into the limitation of ANSYS limiting the amount of nodes and elements you can simulate at once. So there's always something, unless you have a fancy license. So let's see. I also did maximum principal stress, and this maxes out at 4.6 times 10 to the negative second megapascals in the bottom part, which is just that solid steel part. Let's see. For the maximum combined stress in the beams, we get also not too large, 3.6866 times 10 to the negative second megapascals. So that's well under the yield strength of steel. Yeah, so that's completely acceptable. Yeah. Oh, and then force reaction over here is, it maxes out at 17.7 kilonewtons. And that's not just in the y direction. And then over here, we get 18.1 kilonewtons. So it's important to note that the force doesn't necessarily travel across the bridge at the same speed the whole time. It does take 10 seconds to get across, or 2 seconds to get across the bridge, which is consistent with the 10 meters per second specification in the problem, because the bridge is 20 meters long. But it's not, it doesn't travel uniformly necessarily, because it's challenging to split the top face of the bridge into an even number of faces. It's much easier to do it in odd numbers of faces. So this is 9 faces as opposed to 10, which would have allowed me to vary it more consistently. Yeah, but then we also have moment reactions. So we see a maximum of 3.0698 times 10 to the 7th Newton millimeters. So you take 10 to the negative third off to get that in Newton meters, and then you'd get 3.968 times 10 to the fourth. I think. And then on the other side, we get a slightly smaller number. Still pretty big. But again, the maximum combined stress in the beams is still well within reason. Just 10 to the negative second megapascals. Oh, and I should also note that these elements are one-dimensional beam elements. That's why I used a solid and a line body instead of just extruding circles for the truss, which would have led to 3D elements, which wouldn't really make sense for this because we want to do a 1D beam element for the truss structure because it'll be much easier for the computer to solve that way. And I think that's pretty much it. Just for fun, I wanted to see like what the total acceleration in the bridge was over time. Of course, it's still in millimeters per second squared, which is kind of a useless unit, but yeah, very small. So visually, it looks like there's a lot of oscillation, but if you actually scale it to the true scale, they're like you can't really even perceive the vibration. Just give it a second to render. I mean, it's obviously still present, but inconsequential when it comes to the maximum stress, because as it stands, it's not even close to the yield strength of the bridge. So yeah, that's a epilepsy warning. But anyways, you can see there is oscillation. So we know it's simulating the bridge dynamically, taking into account those inertial loads of the elements, right? So ANSYS is taking into account the density and damping of each element. So I think that's pretty much it. Let's see. Yep. Thank you.